Hello, I'm Jinu Shin from KAIST. It's my pleasure to serve as the session chair of this session. First of all, thank you for joining us at this wonderful event. In this session, we will explore the theme of principles for new AI algorithms, featuring insightful presentation by researchers participating in the Global AI Frontier Lab. This session is also broadcast live on the official website of Global AI Frontier Symposium 2025. Now, let me introduce our first speaker. Our first speaker is Professor Mengye Ren from New York University. He will deliver a talk titled Lifelong Concept Learning. Please welcome Professor Mengye Ren with a big round of applause.
Good afternoon, everyone. I'm Mengye. I'd like to talk about lifelong concept learning. So we've all seen great progress of machine learning and AI these days. But while we have huge progress, the training paradigm is kind of weird. What do I mean by that? So we are benefiting from training from random documents on a huge internet scale data. And the training is that we sample a small batch of documents from random over the entire data set, and then the model does not continuously adapt in the real world. The model is frozen. If we have to learn new knowledge, we'll have to essentially retrain the model. And what's making this problem more severe is that today, a lot of us are considering applications of using LLMs as agents. And we've seen an explosion of agentic applications. Essentially, what we do is we use the context window to simulate the perception and the memory of the agent. And we ask the LLM agent to make a decision at each round. But the agent itself is not learning from the episodic tasks. It relies on the context to refine its own behaviors. You cannot learn from one task to another, and the context eventually has a limitation. Not only do you not have an upper bound on the context size, you do not consolidate your knowledge over time. So these are the problems of today's agentic learning. And let's take a comparison to a lifelong learning of a real-world agent. And we, as humans, are real-world agents that quickly adapt to new environments and learn in an open world. We encounter new concepts in an online experience. And these contexts do not just appear randomly, they appear on a structure of this correlation of space-time. They repeat with a naturalistic distribution shift. So our goal of my lab is trying to make machine learning more flexible that can enable agentic learning from a real-world environment. So today's talk is going to be on lifelong concept learning. And first of all, what are concepts? So concepts in common word is a set of common things. Okay, so they can be object classes, different species of dogs can form a higher level concept of a dog. And they can be words, as semantic concepts. They can be events. For example, today's event will become a concept in your memory. They can also be transformation. So when I think of integration or differentiation, they become one solid concept. I do not need to go through the individual mathematical steps. So how will AI benefit from learning concepts like humans? Okay, so first of all, it can now continuously adapt by incrementally accumulate these concepts in its memory. So it enables lifelong incremental learning. It can compress new knowledge in a more efficient way by storing these concepts. And last but not least, it can now planning for a higher level abstraction. So in earlier today's talk by Professor Yang Le Kun, he gave an example of planning a trip from New York to Paris where you have to make high-level planning decisions of these abstract steps. And each of the steps are essentially in the higher-level concept space. So with lifelong concept learning, there are a couple challenges. And these challenges we have seen a lot in the past machine learning literature as well. So first challenge is sample efficiency. So essentially, how can we learn new concepts with just a few examples? We know humans are great at learning new concepts with one or a few examples. These are images from a decade ago where people studied how we can learn these word concepts or image concepts by showing machine learning models with a few examples. And nowadays, these tasks are nearly solved, but we are still facing new challenges in the latest AI models of learning concepts. And new concepts often can occur by having compositions of basic elements that can form new concepts. And so this is an example of a sculpture where you see a fisherman with the head of the fish and the body of a man. Okay, so this new concept immediately struck in my head and formed a new concept. The second challenge is distribution shift. Okay, so in the classic machine learning literature, there is a class of learning challenges called continual learning, where you learn on one task and shift to the next task, and so on and so forth. Okay? So the constraint here is that we do not look back in the previous task, and there's a memory and computation constraints. In the past, there have been a lot of approaches addressing this challenge, okay, including memory replay, architectural design choices, and data regularization. But the structure is often considered quite rigid and less naturalistic. So if you take a look at the continual learning setup, you have one task followed by another without any look back. Okay? But in the human learning setting, we have tasks interleaved with one another, and oftentimes you repeat and look back at one of the tasks and transition to another one. So there is a more naturalistic task transition in the real world. So quickly today, I'm going to focus on three aspects of lifelong concept learning. Ranging from the concept learning in LLMs and the concept discovery in LLMs, and lastly, how can we form event concepts from a visual stream? So the first work I'm talking about here is how do we generate concept embeddings for LLMs? Now, we know that LLMs are great at in-context learning, but there are still limitations of what in-context learning can do. First of all, if you want to learn a new concept, you have to carry that context around you. Okay? We cannot just consolidate that knowledge into one embedding vector, and then now we can basically generate that knowledge through that one vector. And this is essentially what we want to do. Okay, so we are trying to learn this new word that has never occurred to the LLM before. And what we want to do is compressing that into a concept vector so that later on it can learn to generate new sentences using that concept. Okay, and we found this way is much better than in-context learning. And one of the tasks that we try is a GRE verbal reasoning task, where the language model has not seen that word before, and they have to try to do multiple word choices to see which one fits the original sentence better. And the horizontal line you see is the number of examples that we provide to the LLM, and we significantly surpass the performance of in-context learning. And the performance keeps growing with more and more examples. So this is an example how we can generate concept embedding vectors, and this consolidates the knowledge much more efficiently than in-context learning. And we can apply similar concept learning ideas for a task level concepts. So now, given a set of input and output examples, we can define a concept being the transformation that maps between x and y. Okay, so this is an example that fills in the intermediate grids with yellow color. And we propose a new idea called context tuning, where we tune the demonstration examples, the x1, y1s, with a different embedding vector. And now at test time, we're going to use the tuned examples to prompt the LLM to generate these concepts. As a comparison, you can find out our methods performs better and more efficiently compared to the baselines, including in-context learning, which is at the lower left corner. I should mention that there are quite a few ongoing collaboration, and I'm part of the Global AI Frontier Lab, and we're exploring a lot of different ways for lifelong learning in LLMs. My second part of the talk, I want to mention how we can let LLMs to discover new concepts. So previously, we were given a new concept, presented to the LLM, and asked it to memorize it. But if there are many items that are similar in a sequence, ideally, the LLM should already discover that something is repeating for many times. So we want the LLM to capture that. So traditionally, this type of task is achieved from the clustering operation. And in the computer vision literature, there are category discovery and point cloud object discovery, which essentially cluster the point clouds or the images into bigger classes. And in this work, we propose something different. We propose in-context clustering, which basically says there are a few tokens in the sequence that belongs into a higher level concept. Can the LLMs group them and capture this new concept? And it operates in two settings. The first one is a zero-shot setting, where we just present the sequence to the LLM and ask it to group them into classes. And the second setting is that we fine-tune the LLM on some base classes and then test them on a set of new classes. So here is a comparison from in-context learning and in-context clustering, where here, in the sequence, we do not give the label of each image or each text and ask them to group it later in the output sequence. And this can be applied naturally to a lot of image tasks as well. We can use the vision encoder to encode the images into tokens, and then simply ask the LLM to group these images into higher level classes. What we found very interesting when the LLM is performing clustering is that the intermediate attention layers often capture the concepts very well. So this is a visualization on the pairwise attention scores. And what we found is that the middle layers already form blockwise attention structure that corresponding very well to the class labels. And we are currently exploring ways to exploit this attention structure better for concept discovery. Lastly, the LLM for clustering offers very good flexibility for identifying clusters based on different conditions. And this cannot be achieved by traditional clustering such as k-means. So for example, here we can ask the LLM to group these images based on classes, and it will produce one set of grouping. And we can also ask the LLM to perform grouping based on color, and then it can produce another set of grouping. And lastly, I'd like to talk a bit about how do we form concepts from streaming video data. And we want to basically connect the sensory stream at the bottom. So here is a comparison between IID learning, where we benefit from a massive internet scale data, so we can just apply a global loss at the very top. And I believe something more fundamental needs to be changed when we're dealing with a data scarce regime, where we have naturalistic, embodied, continuous visual stream fed into the bottom, and we have to design an entire learning pyramid so that we learn efficiently under distribution shift. In the first layer, we have to learn good representation from raw video. And then we group things into parts, into objects, or into temporal segments. And lastly, we keep an incrementally growing memory so that it can accumulate new concepts flexibly. Speaking about learning latent representations from videos, we have a serious work that learn the network from scratch using motion cues. There are two ideas here. One is we want to improve the high-level recognition in the network, meaning that letting the network understand objects better. But in the meantime, we also want the network to understand motion better. And we believe that better motion understanding can also improve object recognition. So we designed this learning algorithm, self-supervised learning, by jointly learning motion and semantic understanding. The video you see here is a network that's learned without labels from scratch by watching self-driving videos. And then we do a probing, semantic probing for semantic segmentation. And you can see the representation learns very well for these different object classes. So now I want to be able to learn event concepts from streaming videos. So if you think about, you have a representation at the bottom, which provides an encoding. And then in your memory, you try to group them into event classes. So if I try to recall my trip to Korea this time, I get off from the airport, right? I took the train and get to the hotel. So these parts of my memory are segmented into different parts. I do not remember the individual frames in my trip, but I remember different checkpoints of space-time. And this is what we want to build as well. We want to perform event segmentation to save the key moments. And the content in my memory may get replayed and consolidated back into my representation. So the two are mutually feeding information from each other. And lastly, we consider this event a streaming learning setting. We play the video exactly once to the network without looking back. The network may have a small memory for replay for itself, but we do not play the video multiple times like in training large networks. So the key question here is that can event concept emerge from the streaming video learning? And can event concepts benefit representations? And the answer is yes. So our model is really simple. We group the visual representations based on a simple greedy clustering algorithm, and we save them into a small memory buffer. And next, we are going to learn the memorized event concepts together with the new video frames through an SSL learning algorithm. And here is the result. We train our network from SayCam, which is a baby headcam video data set, and KrishnaCam, which is also another first-person video data set. Not only were we able to beat the baselines that are simple SSL algorithms and continual SSL algorithms, we're also able to beat the IID baseline, which is learning SSL from shuffled frames. And this is by no surprise, because we're leveraging better the spatial temporal structure than the IID counterpart. And here you're able to see that we are able to merge bigger event level clusters. And the cluster we're seeing here is a person beside the task. And they could occur multiple times in that video, and we're successfully capturing that. And currently, we're also having an NYU KAIST collaboration looking at visual word learning from baby's eyes to see if we can efficiently learn these object-level concepts associated with the word transcriptions from the audio stream. So in summary, today I present an entire framework for lifelong concept learning. The goal is to address the challenge of sample efficiency and data distribution shift. We go from the representation level, and then we merge them into event clusters and semantic clusters through LLMs in context clustering. And lastly, we can further consolidate it into tokens. And before I end, I'd like to acknowledge the work from my lab, and this is a photo. And this work won't be possible without the support from the Global AI Frontier Lab. So I also like to thank them. Thank you very much.
Thank you again, Professor Mengye, for your great talk. So our next speaker is Professor Sunju Kim from Yonsei University, and he will give a talk titled Understanding the Streaming Videos. Please welcome Professor Sunju Kim with a big round of applause.
Right, so hi, my name is Sunju Kim from Yonsei University. I'll be talking about understanding streaming videos. And I think there's some close relationship with what Meng just said on the understanding streaming videos. I should talk to you afterwards. All right, so I'm going to start by talking why streaming videos. And I'm going to talk my story about when I actually started to work on streaming videos. So about 10 years ago, in 2016, I had this grant called Query-Based Video Highlight Generation. So basically, the goal here was we had a baseball video, and then from the baseball video, user will give some type of query, like show me the scoring footage of Team A from the game last night. And then from the language description, the AI system will give you query-based highlights. And this is 10 years ago. So the context is this is way before the era of LLMs and even transformers. So we had to rely on old-fashioned NLP and computer vision technique to deliver query-based highlights. So anyway, so starting from this project, we started to work on streaming video understanding. And if you think about videos, right, videos are basically inherently streaming. Right? Human vision is streaming. So our vision system, the input is basically a streaming video. So all these videos from surveillance camera to robots and everything, we need to understand videos in an online fashion, the streaming in a streaming fashion. Unfortunately, a lot of computer vision works on videos really didn't work in a streaming fashion. They were all offline algorithms. So what I mean by that is one of the most popular tasks with videos would be action recognition. So in action recognition, you're given a video sequence from the start and to the end of the action. So very nicely cut. So given those video sequences, your model needs to figure out the class of actions in that video. So that's nice, but you can't really use this in a streaming fashion because you don't even know when the action starts and then when the action finishes, right? And another very popular task in computer vision is temporal action localization. So in TAL, basically given the whole video, you can watch this video many times as you want, as many times as you want. And the goal here is to figure out when an action starts, when that action ends, and then figure out the class of actions. And this is all offline. You can watch the video several times. You can even do a lot of post-processing afterwards. So that's good, but then again, you can't really apply temporal action localization for a streaming task. For streaming tasks, there's a task called online action detection. And what it does is it basically classifies every frame. So it predicts the action per frame. So every frame, you basically classify this is running, this is walking, waving hands, and so on. So that's a streaming video understanding. Only problem is it's doing this on a frame-wise level. So you don't really know if these are same actions or different instances. So OAD, although it could serve as a baseline, isn't really totally useful for streaming video understanding. And obviously, there's also another task called online detection of action start, which is really only interested in finding the start of an action. So we saw all this task was good, then again, not enough for streaming video understanding. So we came up with a new task called online temporal action localization. So the end goal is very similar to temporal action localization in that the goal here is given as streaming video. We are going to figure out when an action starts, and then as soon as this action finishes, we detect the end of the action. And then so we kind of have an action cluster. So this is kind of like an instance segmentation only in temporal domain. And obviously after that, we are going to classify what type of action just happened. So this is our first work where we came up with the task definition with some baseline. We also came up with our own algorithm based on imitation learning. And here's one of our results. So we are watching a live baseball game. Now we can basically, as soon as an action starts and ends, we can figure out when that instance happens. And as you can see, we can also know what type of action is happening on the videos. And so that was our first work, and we kept on doing research on streaming video understanding. And our latest work on streaming video understanding is obviously was with using the VLMs, which is what everyone seems to be doing now. Okay, so this was presented last week at ICCV, and there are several keywords. So the first keyword is obviously streaming video. Another keyword here would be hierarchical. So if you think about an action, there are different levels of action. So for example, here, from here to here, the whole video is really about repairing the bike. So that's on a very high list level of what an action is. But then again, during repairing the bike, there are sub-actions. So on the second level of the hierarchy, you have the changing the wheel action, repairing the brake action. And if you go a little bit lower, there are even sub-step of actions like lifting a wheel, tightening a bolt, and so on. So when you do action understanding, we need to look at actions on a very hierarchical level. We need to understand all levels of actions. Okay, so that was our hierarchical keyword, and obviously last keyword would be using the vision language model for generalization purposes. Right? So the VLMs are really great at generalization, so why not use them? Okay, so basically, since I don't have too much time, I'll just give you a very brief algorithm. So basically, we are given videos. This is basically streaming videos. Every frame is keep coming to us. And then we have a very light streaming models where each of this model is responsible for just detecting the actions. It doesn't classify anything. it just detects whether an action started. It also kind of monitors the progress of an action, and it would also know when the action ends on a different level. So from ultimate goal, step, and sub-step. So we rely on the streaming models, which is basically doing temporal segmentation of actions. And so if we have an action start with an end, we'll basically save the frames in our context memory. And then if we have all the necessary information in our memory, then we call VLMs. We just give several frames to VLM, like ChatGPT, and then it will basically say, well, it's loosening the bolt, it's removing the wool, and so on. So we rely on the generalization capability of the VLMs. And one might ask, why not just rely on the VLMs? All the processes here, why do we even need all these streaming modules and everything else, where you could just call VLMs every single time? Well, you could do that if you have a lot of money, right? Like calling VLMs every frame would cost you a lot of money. So basically what we are doing here is a cheap model. We are basically using a very lightweighted streaming model to decide when to call the VLMs so we could kind of save money, I guess. Right? So one thing I would like to notice on our streaming model, our streaming model comes from our previous work, which is called Mini Road. And I'm not so sure if Professor Kyunghyun is here, but he'll be proud. So we are just using RNNs or LSTMs, or maybe GRUs. So what we have found throughout the times we've been working on video is RNNs are really good at videos. And the idea here is when you are trying to figure out the actions in videos, you don't really need a long context. It's a little bit different from languages, right? What I do right now, like waving hand, has no correlation of what I did an hour ago. It has no correlation. So if you visualize the attention or the heat map from different frames, most of the attention is only a few frames away. So RNNs can be really good at detecting the actions on a frame level. So if you compare from all, like this online action detection is frame-wise action classifier, and you can see previous SOTA models are all obviously using the transformers. But then again, we're just using a vanilla RNN, nothing fancy. We're just training it better. And we achieved the highest score. If you look at our model size, it's just like a tiny bit of this heavy transformer models. And obviously, we are really, really fast. So no need to not use RNNs for doing frame-level video understanding. So that was our observation. So we are relying on this very lightweight RNN-based streaming models just to figure out when to call the heavy VLMs. Okay? So this is our demo of the hierarchical video streaming video understanding. And if you notice the result here, it doesn't really align with the video. There's about 2-second delay here. And the delay is actually calling from the lag of calling GPT and getting the answers back. So there's a little bit of delay due to the lag of calling the VLMs. But as you can see, it knows different levels of actions from streaming videos. And then, of course, as a whole, it knows that it's preparing a pasta with salted vegetables. So that's our current, or maybe even a past work, since we already presented this last week. So where are we now, or what am I working on right now? So if you look at the capabilities of large language models or vision language model for video processing, it's very limited. So if you ask GPT, can you actually process streaming videos? It says no. Officially, we don't really process videos. There is a way around that by having few images as a sequence, and you can ask GPT. But then again, it really doesn't process streaming videos. Gemini, on the other hand, does, it does actually do process streaming videos in a very limited fashion. It could probably process about an hour-long video with the speed of 1 frame per second. So it does, but then again, it doesn't. All right, so why can these large models handle streaming videos? Well, the cost. Right? So we all know that they're all based on transformer-based architecture. But then again, if you tokenize all these frames for long videos, and then if you run attention on those, there's just no way you can do this. So how are we going to basically overcome this issue of transformers and videos? There may be several ways to do this. The first thing we're looking at is why not go beyond transformer? Can we come up with a very new architecture, especially for processing streaming videos? As Professor Jan Lukun said, he said many things, but here, as he says here, once you put video understanding, right, the inference costs are going to increase to unmanageable size. So we probably need much more efficient architecture if you want to run videos. So what can we do? Well, we are working on using state space model for streaming video understanding. So this is with a collaboration with Professor Arbagu from CMU, the Mamba guy. So we are trying right now to come up with a new backbone model to process streaming videos, and hopefully maybe next year I can talk about, hey, here's this new backbone for streaming videos that's as accurate as transformer-based, but much lighter. So that's one thing that we're pushing for. So hopefully we would end up with good results. And what's my ultimate research goal? And maybe this is where computer vision is going. If you look at what's happening in computer vision, it almost looks like we have reached at a level where we have done enough, but in a separate test. There is segmentation, there's 3D modeling, there's classification. So all these different tasks, in all these different tasks, we have reached almost the top. But then again, this has to be merged at some point. So I think what the direction is going to be like is from streaming video, we will need a model to do semantic 4D reconstruction. So we, with new models like VGGT, there's very strong 3D modeling models, right? And this would have to go to another axis, the temporal axis, to do 4D reconstruction. But then again, we would also need to add semantic to this. It's not just enough to have the X, Y, Z coordinates of our 3D world, but we also need to know the context or the semantics of those objects in 3D. For example, if I have my AR or all this meta glasses on and I'm just wavering around, taking videos, and after a few hours or maybe after a few days, if I ask a question like, where did I leave my glasses at? The AI model would be answering, not in coordinates, but on the table in your kitchen kind of thing, right? But here, so the model, the computer vision model, I don't know if it really needs the intelligence. In a way, what I'm saying is, I think we can leave the intelligence to LLMs. They're very good at doing Q&A. They're very good at generating explanations. So this vision model would be, what this vision model needs to do is come up with the right representation that actually explains the semantic 4D world around us. And one thing missing from this, our concept here, would obviously be memory. How do we create memory of things that had happened? How do we, add or remove, retrieve events from those memory? Would be another very fascinating direction. Okay, so although I think I have about 2 minutes left, that's it for me today, and thank you for listening. Thank you.
Thank you again, Professor Sunju Kim, for your great talk. Okay, next speaker is Professor Julia Stoyanovich from New York University, and she will give a talk titled Responsible Data Engineering. Please welcome Professor Julia Stoyanovich with big round of applause.
Okay, I'm starting. So welcome everybody, and I'm sorry, but I'm half asleep, so I'm going to be using my notes for this talk. I apologize. I promised to give a talk on responsible data engineering, but based on the conversation that I have been hearing here today, I felt that I really must take a wider lens, and instead, or in addition, speak about responsible AI in general, and responsible AI beyond the principles, about building a regime of distributed accountability. And part of this is going to be responsible data engineering, but again, when we use terms like trustworthy, inclusive, responsible AI, we actually need to be on the same page about what that means, and I lacked a lot of that conversation during the earlier part of the day today. So my name is Julia Stoyanovich. I direct the center at NYU called the Center for Responsible AI. I'm also a computer science and data science faculty at NYU. And I take part in the inclusive AI stream of the NYU KAIST initiative and in the responsible AI component of the Global AI Frontier Lab. I mentioned that I run a center at NYU called the Center for Responsible AI. Our goal is to make responsible AI and AI synonymous in a not-so-distant future, and I will tell you specifically what I mean by that. But for now, please take a look at our website, where you will find a lot of our technical and socio-technical work at the frontier between AI and society. And you will also find a lot of work here on education, training, and public literacy, which I will also motivate through the 20 minutes that I have. And also a lot of our policy, regulation, and generally work around how one sets up guardrails around the use of AI in society. Ukraine was mentioned earlier today in the context of it's now okay to use AI in autonomous weapons. I want to say that I disagree with that strongly, and that I have been running a program together with the country of Ukraine called Responsible AI for Ukraine, where we do research projects with Ukrainian students, and none of them so far have been on lethal autonomous weapons, like lethal drones. So to start the actual part of my talk, I'd like to give an example. And the example goes as follows. In late 2023, New York City rolled out an AI chatbot that was built by Microsoft to replace humans in giving advice to small and medium-sized businesses. The idea was straightforward. Make it easier for entrepreneurs to navigate local regulations, from permits to employment law, by typing questions into a chat window instead of calling city offices and waiting on hold for a while. But within days, the system began producing some remarkable advice. It told employers that it is legal to fire a worker who complains about sexual harassment or does not disclose a pregnancy. It also gave some really, really hilarious and incorrect advice to restaurant owners. For example, it helpfully suggested that they could still serve cheese to customers if it had been nibbled on by a rat, as long as they informed the customers of the extent of the damage. And this was not a one-off mistake. The chatbot also contradicted the city's own waste regulations, advising businesses to put trash in black garbage bags and to skip composting, and this is all illegal in New York City. So in just a few prompts, we saw errors that spanned labor law, health code, and environmental policy, each of which carries real legal and financial consequences if this advice was followed. When asked about the problem, our mayor, his name is Eric Adams, defended the system. He said, quote, "It's wrong in some areas and we've got to fix it," and emphasized that it's just a pilot program. Anytime you use technology, you need to put it into real environment to iron out the kinks. Now, Adams has been a strong advocate of using technology in public services, and very often, more often than not, this technology has been untested. For another example of this, in addition to the chatbot, is when the city deployed a 400-pound robot in the Times Square subway station, and it was meant to help deter crime. But 5 months after that, it was dismantled because New Yorkers were complaining that it's just standing there and not doing anything, and it also wasn't able to climb the stairs. So it was a completely useless, very expensive piece of equipment, essentially. And here we see a pattern, an eagerness to deploy automation into civic life before establishing accountability, before clear guardrails, validation, or channels for feedback even exist. And this is not just a funny story about bad chatbot advice. It offers a glimpse into what happens when responsibility is displaced, when a city delegates authority to a system that doesn't understand context, law, or ethics, but still speaks with institutional authority. So it's really tempting to laugh this off as a bad AI story. A glitchy chatbot saying absurd things about rats and cheese. But the problem here isn't the AI. It's the decision to deploy it, to let a system that hadn't been validated speak with the authority of government. No one built in guardrails, no one made sure that there was a feedback loop, and no one was clearly responsible for what the chatbot said. So this is not a bad AI story. It's a missing accountability story. And that's where I'm starting today, with the idea that responsibility doesn't disappear when we automate. It just becomes distributed, often invisibly, across technologists, decision makers, institutions, and the public. And when accountability is distributed but invisible, it fails. The goal isn't to assign blame or to centralize control. It's to make responsibility visible and deliberate, to show where decisions are made, what values they encode, and how they can be adjusted. That's what turns responsible AI from a slogan into a practice. Responsible AI is about exposing the knobs of responsibility to people. So at this point, I would like to take a moment, 2.5 minutes really, to make this idea tangible. I would like to show you an animated short called Alice in Algorithmia that follows a regular person through a day shaped by AI. As she goes through her day, Alice moves from being surrounded and directed by this technology to regaining agency and control. It's a story about seeing the knobs of responsibility and learning to turn them. All right. So I hope this woke you up a little bit, maybe. So now let me continue with a positive or a potentially positive example. And this is an example from medical imaging, a field like in many others, AI is all the rage. Cutting-edge systems are starting to be used in clinical practice to improve diagnosis and prognosis capabilities. One example is fast MRI. MRI stands for magnetic resonance imaging. This is a collaboration between the NYU Medical School and Meta AI. These are rapid MRI scans constructed with the help of AI. They need 4 times less data and are 10 times faster to make than a traditional MRI, which can mean the difference between a patient getting a scan or avoiding one, especially for those who are claustrophobic, or in a system where MRI machines are in short supply. In short, fast MRI can reduce cost and expand access to medical imaging, a case where responsible design can meaningfully improve care. We're also seeing remarkable progress in AI for cancer diagnosis and radiation therapy, where models perform on par with the best human pathologists, and human AI teams outperform either one alone. But these successes don't mean that these systems are flawless. The radiologist knows that they are ultimately responsible for diagnosis and treatment, and this is what makes these systems work in practice, decision-maker readiness. The radiologist knows when to trust an AI and when to question it. And this balance, automation that augments rather than replaces, is what responsible AI looks like when accountability is built in from the start. When we think about accountability in AI, we have to widen the lens and look at technology together with its stakeholders. Not just the code or the model, but the people, institutions, and environments that surround it. A stakeholder is anyone who is impacted by a system directly or indirectly. In healthcare, that means patients and families, caregivers and clinicians, hospital administrators, insurers, pharma, and the technologists who build these systems, and also ultimately society and the planet that bear the costs. Once we identify stakeholders, we can ask what is at stake for them. Every AI system redistributes something: risk, access, opportunity, or control. So the ethical questions become concrete: who benefits and who is harmed? Whose sense of fairness or justice is being served? And who retains agency, the ability to question, to intervene, and to decide? In healthcare, these dimensions are once again concrete. The benefits are faster scans, earlier diagnoses, better access to care. The harms are missed cases, over-reliance, or inequities in who the system serves well. Fairness and justice mean ensuring quality care for all patients, not just for those represented in the data. Agency and control mean that clinicians understand when to trust AI and when to challenge it. These are the dimensions that connect ethics to accountability, and that responsible AI must make visible. So how do we go about a distributed accountability regime in practice? We need 3 pillars that are represented on this slide: technology that embeds transparency and responsibility, guardrails in policy and oversight that define the boundaries of responsible use, and education, training, and literacy that build literacy and readiness across roles. Together, these pillars make accountability work, not as an abstract principle, but as part of how AI systems are designed, governed, and used. So now, in the remaining 5 or so minutes, I want to give you an actual technical example. So now we're switching to responsible data engineering, and specifically the stakeholder to whom we are exposing the knobs of responsibility is a technologist who is building systems. So in this case, we're going to consider Anne. She is a data scientist at a human resources department at a large retailer. She's building a model to recommend compensation offers to new hires. Anne follows standard practice. She splits her data into training, validation, and test, then pre-processes it. As part of that, she interpolates missing values, trains and tunes the model. And when evaluating the accuracy, she notices a problem. The model performs worse for older applicants, often predicting lower salaries than they deserve. A technical disparity is now producing a real harm. How can Anne understand the cause and correct it? That's where our tools, the technologist snobs, come in. Anne traces the issue back to data preprocessing and realizes that the feature number of years of experience is missing more often in older applicants. Because she used the default imputation method, those missing values were filled in with the average experience, effectively skewing applicants younger. And the real problem is the hidden assumption that data is missing at random. In reality, people may leave that field blank to avoid age discrimination, so older people are more likely to omit signals that would allow the system to reconstruct their age. And so a technical shortcut in the pipeline embeds a social bias, showing how defaults can quietly turn into discrimination. In Anne's case, the bias came from a default imputation choice that no one questioned. We developed an evaluation methodology and a software library called Shades of Null that helps data scientists like Anne evaluate how different imputation strategies affect accuracy, fairness, and stability, turning missing data from an invisible step into a visible decision point. In other words, Shades of Null makes it possible to practice accountability right where bias often begins, in data preprocessing. We also developed a tool called ML-Inspect, and it's a methodology for data distribution debugging. ML-Inspect traces how data transformations affect model behavior. For example, how a simple filtering step can quietly change the proportions of demographic groups without the data scientist realizing it. ML-Inspect makes these effects visible, helping technologists detect and fix issues before they turn into fairness or validity problems downstream. Another methodology and tool we developed is called Virni. This is a system for responsible model selection. It supports data scientists in exploring and optimizing pipelines, exposing every modeling choice from parameter tuning to fairness evaluation. Virni helps technologists see how performance, fairness, and robustness trade off, turning model selection into an accountable, transparent process. The last piece of work in this area that I will highlight was done jointly with Stephen Wang at KAIST and with his student Daniel Huang, who is visiting us at NYU right now as part of a program that IITP supports. So here, we observed essentially that the way that you represent data is going to change what kind of an explanation SHAP, a popular library, produces for a data point. So, for example, your explanation, the true explanation, may say that age is the most important feature, you see this at the top, when a lending decision is made. And a lender, a bank, may be afraid that you're going to sue them for using a feature that you should not be using to decide whether somebody deserves to get a loan. And they can manipulate the representation of age, bucketizing it in a particular way, so as to demote age importance. So this is an example where seemingly innocuous data preprocessing operations actually help mask discriminatory or unlawful behavior. There's a lot more work that you can take a look at under this umbrella of data-centric and responsible AI and responsible data management. We also have done work on privacy-preserving data synthesis that I want to highlight quickly. And this is for a different stakeholder group, for scientists and decision makers who rely on data to draw conclusions and set policy. And a turnable knob for them is when to use synthetic data generation with differential privacy and how to set the privacy parameters. We introduced in this work a notion of epistemic parity as a new evaluation principle for private synthetic data. Rather than asking whether synthetic data preserves summary statistics or model accuracy, we ask a simpler and deeper question: do the same analysis conclusions hold when you use synthetic data rather than real? I'm out of time right now, so I'm going to stop here. You can take a look at our website for lots more on differential privacy. And I also want to just flip through the slides to say that we do quite a lot of work at the Center for Responsible AI on policy, internationally as well as nationally within the United States. Here I'm highlighting an effort with the United Nations Office of Disarmament Affairs that I'm part of on non-proliferation of lethal autonomous weapons. This is a Canadian government standard on accessibility and technology. I've been speaking to the US Congress. This is a recent testimony on DeepSeek and its national security implications for the United States. And I have also been working on methods for disclosing things to people like job seekers before they apply for a job, coupled with regulatory interventions in New York City. Lots of work on transparency and explainability that is stakeholder-facing here, and lots of work on education, training, and literacy that we have been doing, and where I really hope that we can partner with colleagues in South Korea as well. And my next stop this week is Berlin, where I will be speaking about how LLMs work and don't to the general public as part of the Berlin Science Week. So thank you very much, and let's speak offline.
Thank you again, Julia, for your great talk. So next, our next speaker is Professor Jaesik Choi from KAIST, and he will give a talk titled Explainable AI to Analyze Internal Decision Mechanism of Deep Neural Networks. Please welcome Professor Jaesik Choi with a big round of applause.
Hi, everyone. Thanks for introduction, Jinu. So I'm a professor at KAIST and also director of Explainable AI Center, and I'm a CEO of Iniji, a startup company Iniji. So briefly, I will try to introduce why we need explainable AI and how the Korean government and researcher in globally try to enhance the explainable AI technology and try to explain what my research lab and the center try to in-depth to do the explainable AI research in recently. So explainable AI, in my opinion, is important because most of real AI systems are less predictable, like providing the less predictable outcome. So if we compare to any other stuff without AI, something like smartphone and the car and other like a remote control, they have a deterministic mechanism, and their outcome is like most of the cases predictable. But in many cases, if we ask to LLM or AI system, in many ways, we are asking the question we did not know exactly well. So in many cases, even if actually the outcome is deterministic, in the perspective the asker, so the result is less predictable. So because of this, the less predictable outcome, we need to verify the result is good or not, or whether this is a hallucination and so on. So in many cases, if the user are not really certain, then they need to ask question why this decision is made. So I briefly introduce how Korean government try to enhance the explainable AI research. So this is a part of long-term agenda to make the trustworthy AI in Korea, including responsible use of AI and trustworthy society and a safe cyber nation. Of course, actually, this is ongoing agenda. And as an example, so Explainable AI Center established in 2017 in July, and the term is expanded until almost 10 years. So to have a lot of research effort and the collaboration not only in the Korea but also in the external, international, institute and so on. So I will try to briefly explain what we do here. So as an example, some of the textbook and many paper, and especially the engineering effort that Korean government and society emphasize on is made in the manufacturing and the healthcare and the finance and the internet mobile service and so on. Of course, actually including the open source community. So as a first example, so we try to make the agenda like a position paper with explainable AI. So one message is, so there are long-term trade-off between the explainability and the performance. And some people say that when the AI algorithm is more explainable, and probably the performance is lower. That is actually what people thought. But after like a long time of research, and the people figured it out that when the explainability emphasized during the verification procedure, and then the generalization error is reduced, meaning that generalization performance is improved. That is actually what actually we concluded. And this is recently, like this year, getting an award from the Chinese International Congress of Basic Science as a Frontiers of Science Award. So we collaborate internationally to make the a review paper and making the agenda to what is open question and what we have been done and what is actually less done and in different discipline, and this is actually also published. And another one good, I think actually good, so I should not self-evaluate, but somehow another important agenda is international standard of XAI. So as you say that in almost 5 years ago, 2020, some of actual Korean researchers initiate to make the international standard of explainable AI. And there is actually long-term review and the discussion and so on is finally and published in the last month. So this is the first official international standard, which is led by some of the Korean researchers, including Professor Jae Lee in the University of Seoul, who are participating in our explainable AI research, and now the first international standard. Actually, this standard is really important with any other GDPR and the UAI Act and almost regulation. So how do you actually give the regulation for the explainability? And then we need to have a standard. And this is the first standard. And I think actually many people will branch out from this standard for the healthcare and automobiles and the manufacturing and the other type of one. And we try to do the open source community to try to make this development for the open source called plug and play explainable AI, because using the explainable AI is really hard because we need to understand algorithm and the parameter and the AI and the domain and so on. So a lot of people have hard time to tune the parameter, even for the simple a line and the shape and so on. So what we provide there is, as you are using device easily with the USB, so we are providing frameworks when a user just plug in the AI model, then our framework automatically understand what model architecture used and which algorithm, explainable AI algorithm can be served, and evaluate which algorithm is good, and based on the user criteria, recommend which algorithm is actually good for the user usage. And that is actually what we provide in the open source. And there are some criteria like correctness and the continuity and the compactness and so on. This can be tunable by the user. And as an example in here, if we provide AI algorithm and an image of bird and the individual algorithm are evaluated, and based on criteria which algorithm is best is selected by the AI algorithm, our plug and play XAI automatically. And this, as I say, that is open source, and many people can participate and use freely, and actually based on the license, and also we contribute to the expansion of open source society of XAI. Another one is commercialization. So we, me and with some of my colleagues, find a startup company called Iniji, which is explainable AI-based prediction and control for industry startup. And this startup is selected as one of the a national strategic technology company. So we have a lot of reference now, and also we have a lot of successful operation in real world. And of course, after numerous failure, so we can apparently say that our algorithm has a lot of real world data and the experience, and almost already verified in the one. That is actually the reason why we are getting the certificate for the national strategic technology and so on. But actually, this is a brief summary of what we are doing in the macro level. Let's try to go into the detail for the algorithmic level. So the question, so what we are asking, so what we are curious about the deep neural network model, AI model. So the question is, we wish to find the generative boundary, nonlinear generative boundary of deep neural network. So something like this magnitude, magnify the internal mechanism. So as an example, we try to find the internal decision boundary of deep neural networks. So as an example, we are expanding all the vectors in the, we are distinguishing the positive and negative and so on, and asking question, what if? So second vector value, the second value in the vector, change the sign from the positive, from the negative and negative to the positive and so on. So we need an algorithm to find the non-linear space in the manifold, try to explore checking the decision boundary of this internal mechanism. But this is not really hard because thousands of dimensions and the thousands of actual decision boundary and so on. So we are using some of the nonlinear exploration method which is used in the robot planning called the RRT, and finding the extensive search mechanism to find the refinedly find the image sample that is included in the decision boundary. We call that as explorative generative boundary aware sampling. So, and we extend this idea a little bit further. So in the generative neural network, so how can we find the a node which make a artifact unique? Something like not only for this generative model, but also in the LLM. So for as an example, we have a lot of transformer unit which make not so politely or ethically right utterances made by the unit. So the thing is, we are finding automatically those artifact generating unit and finding and reduce the activity of those and verify that the artifacts generated image are correctly automatically well. So, and another question that we made by analyzing this internal mechanism, so we are asking questions. So which manifold area is more possible or better to explore more? So in terms of creativity, so creativity is kind of really broad term in here, but which area is less populated in terms of samples? So the thing is, we define the a metric called the reality metric. The intuition is something very simple. So based on all the real sample that we map in the manifold, and we are finding K or N nearest neighbor boundary. You can see the a blue circle. So meaning that if we have many real sample in the nearby, the circle is small. And if there are not so many sample nearby, then we have a bigger sample. Then whenever a new sample come, then we are trying to find the minimum size circle that include a fake sample. Then if the fake sample is included by the real big one, and we define that as a radius as a reality, and the meaning that if the fake sample is included in the small radius, then that is not really rare. But if the new sample is actually included in the bigger sample, then we can say that a new sample is more included in the less explored area. So we define this reality score and try to explore the deep neural network generative model well with some metric like reality and the diversity and the similarity to the reference and so on, and could find that when a new sample comes and by analyzing the internal decision mechanism by using the rarity metric, we can find that the generated sample is more diverse and rare. So you can say that if we generate a sample in the a deep neural network, we can easily find that model collapse happening because similar example made it and several times and so on, but we prevent this rarity metric to prevent the generation is more diverse and creative and so on. So our question and the curiosity going for a little bit further. So try to analyze and understand which deep neural network and the model and the node and act like differently. So one of the interesting question is, so we try to improve and overcome the mode collapse. So rather than exploring, so let's try to change a little bit of the activation of some nodes. So then our hypothesis is, so there would be some node which making directly the creativity, changing the creativity of the node. We call that the creativity node. So try to finding these nodes. So somehow, basically, with some actual experiment, with the frequency domain analysis of individual layer of a deep neural network, and we find that if we analyze and we activate it or we change activation a little bit further of some unit, and we find that the creativity of the diffusion-based model is increased. As an example, then we find this model making the chair more creative, and also first cabin more creative, and so on, and without any supervision. So the individual image in the original and changed to the ours, and the generated image is more creative, diverse, and meaningless. So of course, this is not applicable for all the layer in the deep generative model, but in the specific location of generative model, when we increase activation, then the generated image are more creative and diverse in a way that we can prevent the model collapse and so on. So another one that we are currently focused on is in the same CNN and the generative model, try to find in the concept, the beginning of a concept and the end of the concept. So of course the end of a concept is related to the polysemantic something, but the thing is, so we are trying to analyze in the path from the input to the final outcome. So where the specific object is, try to catch the beginning of the object detection, end of the object detection, say something like the chair or eye or a head and so on. So as an example, to find this, so we are trying to analyze individual neural network, the consecutive neural network, when these individual units are correlated each other in activation, with any activation, and also when they are correlated with the same type of the category or input and so on. We define that as a neuron sensitivity score and the semantic flow score, so on. And we could find then identify automatically with the individual object. As an example, if we try to find the eye object for the specific unit of the dog, and this is actually captured by the red unit. And if we try to find the tail, where the tail is activated, and we are finding this from the blue node. Actually, the beginning of the blue node is the beginning of the tail, and the end of the blue node or end of the tail and so on. So that is actually what we got. And as an example, we are finding flag and the sky and clock and so on. So this is actually not for LLM, but for the CNN or the DCNN, we are trying to capture this for the LLM research. And additionally, what we are trying to do is we are trying to understand how we can reduce the bias for the individual explainable AI algorithm. So as many of you already effort or know, so explainable AI algorithm has its own algorithmic bias. So when we try to run this algorithm, it has a different result. So of course, actually, this reflects their parameter and the algorithmic preference and so on. But the thing is, when we have a black box, like a black box deep neural network, how we can improve the input attribution score is what we actually try to do. This is one of the examples. DGA is what we generate, which is better than the Google integrate gradient algorithm. So I will skip the detailed algorithm here. But another important question that I wish to share here with the audience is this one. So Shapley value is very famous one, and as a shape is one of the easy to use, famous tool. But when Shapley defined this theoretical framework, and then he assuming that individual player and their reward and contribution are independent. But of course, our input are not independent each other. So our question is how can you compute correctly the input attribution when input are not independent each other? They may sometimes have a positive interaction, sometimes negative interaction, and so on. So positive interaction is when we have a 2 pixels, they have a positive relationship. When you have a 2 pixels, they have a negative relationship, and so on. If we can say that sometimes, so if we go into the group with my a close friend, I have a real a more power, but I have a group with a less friend of friend, and I may have a reduced reward and so on. So we find out that in the positive reward, we can change the Shapley value a little bit in the theoretically, then correct and a better computation. But in the negative way, the Shapley value computation failed actually. So and demonstrate that, and our new theoretical framework actually work in the positive relationship. So finally, even if actually Shapley value has some room to improve, many people use sampling-based Shapley value, and we try to improve this computation by using cache mechanism, which is used in the Kakao Bank. So this is the final slide that I wish to share. So even in the LLM era, so I did not share many of these efforts yet for the LLM, but this explainable AI research is important to identify role of internal unit in the LLM, and find the internal unit which behave badly, and control the internal unit which behave badly in the LLM, and also try to correct this internal unit in the LLM and so on, and improve the input attribution method where the actual bad occurs coming from the LLM, which training data and which input occur, and where those unit is appeared and so on. Thanks for attention.
Thank you again, Professor Jaesik, Choi, for your excellent presentation. Thank you for all 4 speakers in this session for their great talk. We will now move on to the panel discussion, which will be chaired by Professor Joo-ho Lee from KAIST. Please welcome Professor Joo-ho Lee to the stage with a big round of applause.
Hello, I'm Joo-ho Lee from KAIST, and it's my pleasure to serve as the chair for this panel discussion. Joining us today are the 7 speakers who have just presented, 7 panelists, including 4 speakers who have just presented, along with Professor Mengye Ren from NYU, Professor Sunju Kim from Yonsei University, Professor Julia Stoyanovich, Professor Jaesik Choi, Professor He, and Professor Rajesh Langanas, and Professor Stephen Hwang from KAIST. So may I kindly invite all panelists to come up to the stage, and please join me in welcoming them with a big round of applause. Thank you, everyone, to present. So the topic of today's discussion would be foundational principles beyond the current AI paradigm. So I'd like to first hear from all of you the brief thoughts about what could be missing from the current AI paradigm to achieve like AGI, in short.
So maybe I can begin. So I believe there are a lot of foundational paradigms that yet to be discovered. So I will speak for 2 points that's related to my talk. The first one is we really need adaptive intelligence that can adapt over time. So the current paradigm of AI is that you train it with massive amount of data, and then the AI wakes up not knowing what year it is, not knowing where it is, what it is, and it just be presented with a context. And the context is all the information it gets. So this is very far from a really flexible, adaptive intelligence that can operate in the real world, that remembers what happens yesterday, what happens just now. Okay, so that's one point. And the second one is we need a more hierarchical abstraction mechanism. So currently, AI operates on the unit of computation that's typically called tokens. And they are sometimes very granular, which makes it very flexible, but sometimes it's hard to get the abstract concept from there. And it's also very sample inefficient to learn abstract concept. So these are the two foundational changes I'd love to see in the next few years.
I agree completely with Professor Mengye Ren. If I would have to add, memory is, I think, an obvious thing that I don't think we have any idea how we should build memory into these networks. So in a way, I kind of also like the direction Professor Jan LeCun is pushing for the JEPA architecture with the memory. So memory would be one. As I work in computer vision, I think tokenization for computer vision is still a long way to go. For language, it makes perfect sense, right? In a way, language itself is human-made thing that's very natural. It naturally leads to tokens. But the way that people tokenize images and video right now using patches, I don't really know if this is efficient or if it even actually makes sense. So I think tokenization or even representation from computer vision perspective would be something I think I would like to see more developments on.
Thank you.
So I'll say two things very quickly. One of them is that I don't think we should be pursuing artificial general intelligence, and I don't think it's just even a thing. And the second thing I'll say is that I thought that we wanted the three people who didn't speak to actually have more airtime. So I'll cede my time so that they can get the floor a little bit.
Okay. Thank you.
Yeah, so I don't think actually that is really missing, but I'm really curious about how the LLM actually works. So in my opinion, so I typically call that, even if it is not verified, I say that this is neural indexing, something like expanded database. So like, of course, actually previous database is really rigid, but somehow then this new neural indexing system is automatically store the data and getting the data and generating the result with template and so on is what I understand. I try to understand, but this is in the abstract way. But like hallucination is one of the like real kind of goal to overcome. So we'll try to improve. But the thing is, before that, I wish to getting more effort to understand how like a unit by unit internal mechanism or understand those LLM as we understand CNN. Then that would improve the application a lot in many areas, is what I think.
Yeah, I think the current AI paradigm largely depends on pre-training by imitating human text. And whatever we do during post-training, either SFT or RL, is mainly to extract the knowledge and skill the model has learned during pre-training. And if we compare that to human learning, it's much less efficient. And for humans, where we're able to do very sample efficient reinforcement learning, and we don't have to explore all the paths or try out many different actions in the real world, we can simulate in our head at a much higher abstraction. So one breakthrough I would like to see is a more sample efficient way for these models to do RL, and potentially by exploring in some latent space that's much more abstract and efficient than the current exploration in the token space.
Thank you.
I think in addition to everything that was said, we heard about like memory, we heard about efficiency, continuity. Efficiency has another side to it. We heard a lot about sample efficiency and being able to learn from data, but there's also like the efficiency of actually the models themselves. Like we're all having a conversation here, but we're not heating up the room in like a super crazy way by having this conversation. Maybe gives you a hint that there's other kinds of efficiency that can be got there. From like a straight methodological standpoint, I think like interventions play a big role. Like how can you learn from an agent or a model that can make interventions? How can that make you more efficient because you know you've made a change? I think that could help unlock maybe what the next step is rather than looking at just straight retrospective data and then fine-tuning it or post-training it in some way.
Yeah, so just to add my opinion, I agree with the other panelists about the various aspects we should be looking at. I personally am very interested in looking at the data, and so I think machine learning is all about training from the data, and there's a lot of data pre-processing going on before training a model, like how to acquire data, how to label data, and how to augment data, how to sample data, and so on and so forth. And so especially for LLMs nowadays, I don't think we have a clear understanding of like how we're exactly learning from the data. LLMs are trained from a lot of data sources, like the entire web, Wikipedia, encyclopedias, millions of books, code repositories like GitHub, and so on and so forth. But it's very coarse-grained, and if you look at the current literature, the LLM pre-training state-of-the-art techniques try to solve the problem of like domain weighting. They try to find the right weightings to give to different domains. And one of those domains is the entire internet, which doesn't make too much sense for me. And so I think there needs to be a lot of research on how to ensure that we have high data quality and how to pre-process the data. Another aspect I'm interested in is responsible AI. And so it's not just about performance or accuracy. I think in order for LLMs or AI to be used in our everyday lives, we also have to look at fairness, privacy, explainability, and human alignment, and so on and so forth. And so I think we really have to ensure that all of these aspects are satisfied starting from the data.
Thank you to all the panelists. So I recently came across with this podcast, where the Rich Sutton appeared, and he made quite a radical claim there. He actually argued that in his ideal learning system, we won't even need the pre-training. So all we need was just an agent which could interact with the environment and learn to predict the next state of the world and plan the actions. So in this regard, I want to ask further about the pre-training. For instance, do we ever need pre-training, or at least the serious part of it should be changed to Professor He and Professor Langenus, who mentioned about pre-training and sample efficiency. So do you think our ideal system would still need pre-training, or would it even necessary from this starting point?
Yeah, so I couldn't hear the entire question. So is that more about whether we still need to invest in pre-training?
Yes.
Okay. Yeah, so I think pre-training is actually much more important now, because I think earlier maybe in Yejing's talk, she also mentioned that now people are looking at what's really, what is this post-training RL doing, and it appears that they're not always that effective if you don't already have the knowledge in pre-training. So I do think that if we need to maximize the effect of post-training, we need proper pre-training. And also I feel maybe the line between post-training and pre-training is starting to blur now, because people are also talking about mid-training. So it's more about how do you add in the relevant data. If you inject, if the data is more specialized, you want to put that later in the training pipeline. If it's more general, then it will be in the pre-training.
Okay, thank you.
I think maybe one thing I can add to that is like, if you really ask me and you're like, hey, should we be doing like pre-training to solve math? It kind of just depends on how much compute is available. Like in one sense, like math is something that you could span and verify on a computer, and if you could like push it really hard, you could find interesting things that maybe don't require a bunch of like human level pre-searched, like containerized, nice abstractions to do math. On the other hand, that sounds like a crazy amount of compute, and so we probably need to make use of what was learned already to try to, push this a little bit further. But I found myself on the fence of this question because I'm like, for math, if we take all the knowledge that people have about math, will that help us solve problems that people are very bad at solving now, like one of the millennium problems that are out there? I don't know.
Thank you. And regarding the responsible AI system, so I'd like to ask to Professor Huang. So I'm personally very much interested in developing trustworthy AI systems, especially the large ones. So for instance, the current language models are not really well calibrated about their accuracy. I mean, even when they are getting seriously wrong, they often say they are quite competent. So I want to hear your opinion about how should we proceed to make them more trustworthy, reliable, in more detailed way.
Yeah. So if you ask the industry nowadays, what they say is that algorithms are very important, but what's more important is the data and evaluation. And so I think the first step is to be able to properly evaluate whether an LLM is really, knows what it's saying and it's aligned with human values and so on and so forth. So I think there needs to be very, very good benchmarks that can evaluate whether a model is being fair or not. So there's a lot of literature on that, and we also recently published a paper on how we can construct LLM benchmarks using databases. So anyone with a database can basically automatically generate LLM benchmark. And so I think there needs to be a lot of effort, because I think one of the biggest problems in LLM training is that we're not specific enough to, we don't state the objectives as clear enough for the LLMs to behave properly. And so that's the first step. But I think fundamentally, the next step, the solution would be to make sure that it's learning from the right data. And right now, it's very hazy, right? So in comparison to structured data, like text data, like the internet, like it's hard to divide them into different sensitive groups, or like the traditional fairness techniques do. So there needs to be a lot more research on how we can pre-process the data to improve the responsible AI aspects. And so I don't have like a clear solution right now, but I think that's an important direction.
Yeah, I particularly agree that the right benchmarking is important. Thank you.
Yeah, so I recently thought about the thing related to the first question, automatic agent. So what even if actually we talk about the bad thing of RL, so the RL is good when the world is closed, some closed world assumption and so on. But in the open world, it may not work really well, and it may need more effort and not so efficient. But what if actually we are making the scenario something like the agent has some coin, and they are investing this coin with a lot of people, and this investment like environment is kind of somehow semi-closed and semi-open on the assumption. So because we have a lot of data and like a transaction, and then the agent maybe, if we improve, then like quickly learn the behavior of those. And there is actually one thought, and the similar related one is like recommendation for the advertisement, and also recommendation of content like YouTube. And in this area, like less pre-trained, like dependent, automated agent maybe work in the several A, and there would be the like a potential application area of the agent. And as like Professor Wang said, and the responsible AI and the controlling those like effective agent is really important, because so somehow if the agent like somehow like in the controlled way and the less controlled way try to affect the human like behavior a lot, and we need to have a way to find a responsible way to control those mechanisms. So of course, actually, physical AI is not so really direct area, but we have a lot of cyber system or cyber or internet system, which is almost to the agent is close, even if connect to our like physical world and so on.
Okay, thank you. Yeah, I think as the AI systems become more agentic, and as they start to set up their own goals, it will be harder and harder for us to control them. And in the talk by the Professor Yan Kun in the morning, where he showed this outline, and there was this important part of setting the guardrails of the agentic AIs. But I personally wonder what would be some principles that we can apply to setting up those guardrails, because personally I find it hard to imagine like safety guaranteed guardrails that can control any like agentic models. Yeah, so I wonder if any of you have thoughts on this matter, how to set up a guardrail for the agentic AIs. Thank you.
Okay. So, you know, agentic AI is not really all that new in terms of, like I said, we need to create a regime of accountability where people control AI systems and people know in specific roles what it is that they need to do. So when it comes to agents, one of the main things I think we should be asking ourselves is, do we actually want AI to do this thing on our behalf? Or should we be doing it ourselves, right? So I enjoy, for example, reading books, traveling, making art, you know, consuming art, baking a cake, things like this. I don't want an agent to be taking over these tasks, because I don't want a cake that bakes itself, right? So for me, the first thing that comes to mind when I think about agentic AI is, why are we doing any of this? We need to think about the joy of doing science, of living, of building AI, you know, of using AI. So if this thing takes the joy out of life, then what's the purpose? Who's using whom, right? So that's just my thing.
Yeah, I completely agree. So I personally very much enjoy solving Sudoku puzzle every day, and I would be very sad if, I mean, I won't be able to solve it anymore, because like not even just like a modern AI system. So if you put any Sudoku puzzle of extreme difficulty to like a computer program, it will solve it instantly, right? But still, we want to solve it by ourselves, and from that procedure, we find some joy in ourselves. So I think she made an important point. And now, this may be a bit a boring question, because you may have heard of this question many, many times. So do you find any architectural innovation required for the current AI systems? I mean, do we need anything beyond transformers?
I didn't get the question.
So do you think we need some architectural innovation beyond the transformers?
Probably. Yes.
Maybe I think, personally, I think if we anything beyond the current transformer, that would be something related to the long-term memory. So, because I heard two of you mentioning about this memory in the beginning of the panel discussion, so I'd like to hear briefly about this direction.
Yeah, absolutely. So I believe there are many things about transformers. It's just not right. So yeah, exactly. You mentioned the memory part. Currently, it's purely feed forward. So everything needs to be stored in the context in order to be brought up, and this needs to be changed. So there are many ways that we can inject memories by changing the parameters, by changing a small amount of parameters. And recently in our lab, we also found like by disabling some parameters or neurons can also help retain long-term knowledge about new tasks. And you can also learn concept embeddings. In terms of the work that I presented, we can store these concept vectors for long-term storage. So these are some ideas that could potentially change the paradigm of using transformers.
Yeah, I think there will be new architecture. I don't know how soon. I wish I was part of making a new architecture. I mean, 10 years ago, we were probably using CNNs. I think 10 years ago, I think ResNet was introduced. And then obviously there was RNNs, and then the transformer came. There are new models introduced like Mamba, WKVs. They are not as field tested as transformers, but people are working on this. I guess one issue here is big companies has already put a lot of money training these big models based on transformers, so they know this works. I don't know if they'll be willing to spend as much money on testing new architectures, unless they are just sure thing. So I think there's academic side of research for new architectures, and there's another side where the industry will be picking up on a new architecture.
That makes perfect sense. So I'd like to talk about the data quality or synthetic data generation to Professor Hwang. So as you, at the beginning, you mentioned about the importance of the quality data for training. So I wonder about your thoughts on the synthetic data generation. Do you find it promising, or do we need something else than just like their current typical way of letting big models generate data for the next generation and just continue?
Yeah, so that's a deep question. I think in one of the keynotes, I think it was Professor Choi. She was mentioning how to generate like data that looks like the internet, and so I think traditionally, like data augmentation has been around, like studied for a long time, and usually the story is that it helps to some extent, right? So initially it's like very helpful, but you can't keep on like generating infinite data, because at some point you might have a mode collapse, and so you just end up learning whatever you learned again. So that's always been the case for synthetic data. But there are some like challenges, like a lot of challenges within, like in this problem. For example, the problem of bias. I'm very interested in that problem. So if the data itself is biased, then your model is going to be biased as well. So you can focus on like certain subsets of data that are lacking information. So these subsets could be like sensitive groups, like certain people, like based on race or gender, or like age and so on and so forth. And if you figure that there's not enough data, like the data is sparse, then that's the place where you would like to generate some more synthetic data. So I think it's definitely worth taking that approach for once you determine that there absolutely needs you need some more data in for certain demographics. But in general, like I think it would be very interesting if you could just generate brand new data that can further help push the limits of a model. And so I'm aware of some ideas. Maybe like you can let them use reinforcement learning to explore the world and just obtain more data. You can also pay humans to just generate more data as well, real data, but that's going to be pretty expensive. And so I think there's going to be a mixture of these different approaches. Let's generate some synthetic data. Let's try to be very careful and selectively generate real data and so on and so forth.
Can I just say a word to this? So, generative AI is not the only kind of AI that is relevant, okay? There's AI that runs your smart vacuum, and there's AI that takes in patient data of these specific patients and determines for these patients, what do you do? And then there's AI that takes, people's votes and aggregates them using ranked choice voting. All of this is AI. And for many decision support applications, like resource allocation, right, of actual resources to actual people, you absolutely need synthetic data to be able to disclose, for example, and explain what you did. So synthetic data is an enabler of privacy-preserving computation. It's an enabler of transparency of decision-making, right? Because algorithmic transparency relies on data transparency, and you cannot release actual patient data or actual ways that people have voted for candidates or issues, right? So synthetic data is extremely relevant, and I really just want to raise the issue here that Gen AI is not all there is. In fact, for most cases, when you interact with AI in ways that are not like a game, but are real, you're interacting with old school AI systems. And the issues that we're facing there that have to do with responsibility, robustness, correctness, we haven't solved them. We somehow just decided to switch to Gen AI because it's more fun now. But this is misguided. So I want to redirect our attention back to things that actually matter to us.
Thank you. Okay.
Maybe I'll add a more technical point, which I myself don't have an answer. So the use of generated samples or synthetic samples, if you guys remember energy-based models, which is one of Professor Yanlukun's favorite topic, negative samples are the generative samples. So we actually don't want to learn the generated samples. We actually want to push away from the generated samples and to learn the real samples. So now the question is synthetic samples good or bad? It seems like for those energy-based generative models, you want to push away from, but sometimes for LLMs or those more advanced models, generated samples are good. So maybe there is a trade-off. So I wonder what's the fine boundary?
Yeah, so I actually have a similar opinion, but so think about this way. So of course, generated data may be used in the pre-training, in the fine-tuning, and so on. But let's think about using this generated data in the fine-tuning verification phase. Then our assumption is our manifold is not well smoothly connected. Somehow there is a missing part in our learned part, the part. And our hope is generated data can connect this missing part, right? Then the thing is, so we need to have the reason why the generated data with some logic may have a little better connection than what we already have in the missing part. Because naturally, LLM model and the AI model may have an interpolation mechanism in between, and those are really good, but generated data should be better in how because of external mechanism or the other good part of generation thing. And we need to use generated data when this generation has a benefit than the original missing part in the manifold. That is actually what we, at least for me, and the one important part in terms of verification part.
Okay, thank you. So next point is partly due to my personal interest. So I like to ask to Professor Rajesh Saganas because in the morning, again, Professor Yanlukun in his slide shortly mentioned to draw away the probabilistic modeling. So I wonder you are on the same page, or do we still need the probabilistic principle, uncertainty quantification, and so on?
I mean, Jan said imagination at some point, and for imagination, you might guess there's some generation. There's maybe a question whether that generation needs to be explicit or not. Like, there's one view of it where you're like, oh, you just need to take the action. The best way to take an action is maybe like, simulate what might happen and then pick the best one, but you need not be explicit about it. So like, in a sense of the task, I'm like, oh yeah, maybe not. But in terms of like modularizing the problem and the best way that you could get efficiency out of it, then I'd be like, yeah, we keep the probability that's there.
Rather than choosing argmax every time, we try to sample with probability proportional to the predicted outcomes, right?
Yeah, that's right. You want to keep some level of uncertainty about what's going on that might help you explore. There are like decision theoretic principles around it. There's a question of like how computable these are, but if we can get it, we should do it.
Yeah, thanks. And the final question I'd like to ask to Professor Jaesik Choi, because you are the best expert in explainable AI, and it's for me. So I wonder about your thoughts on this explainability or interpretability of these frontier models, because they are getting more and more difficult to interpret what is happening under the hood of these large models. I'm even scary to think about that. So I'd like to hear about your thoughts. Would the principles we used to apply for like fairly old deep neural net would still persist to these larger frontier and more capable models?
Yeah, so of course, actually, I didn't say anything about LLM proving or like interpretability of LLM, but there are a lot of effort in like US and the big tech to analyze those like LLM-based like mechanistic interpretability of this LLM. So I barely think at least in 3 to 5 years we could better understand individual like a mechanism of this LLM-based model, because I think actually in each of unit has a conditional vector-based conditional release of data is what I thought about individual unit in the transform model, because we have attention head whenever there are a vector activation occur, which is not occur in most cases but selectively occur, then the sum of the part of data release, something like important data is coming out and gathering out this. So what the thing is, when this activation occurs in the attention head, and which information is released is one of the key. So I cannot say that in 3 years we can understand whole of these parameters well, but I think if someone specify one unit, then the individual debugger something come out and say that this debugger can identify when this transformer unit activated and which data is released, because we have a finite number of parameters in this unit. So meaning that encoding of decoding of condition and the encoding of decoding of data is what we have to do, and that is actually what I think actually people will try to do.
Okay, thank you. We still have some time, like a minute, but I'd like to finish here. Thank you to all our panelists for sharing their valuable insights, and to everyone in the audience for your attention. This concludes our panel discussion. Please give them another big round of applause. And this concludes all sessions of the Global AI Frontiers Symposium 2025. We would like to express our sincere gratitude to all speakers and participants for being part of today's event. We look forward to seeing you again at our next symposium. Thank you.